There are a lot of games you can play with a billiards table or pool table, and in a way, they all involve mathematics because you're dealing with angles and velocity and trajectories. Today, I want to talk about a mathematical billiard game that's really very simple. You only need one ball and you only hit it once. Each time the ball hits one of the four sides of the table, you write down a letter for that side. L for left, R for right, T for top, or B for bottom. Well, this isn't really a game yet, since anyone could hit a ball and write down bounces. So to make this into a game, suppose a friend gives you a list, like top, left, left, and so on. Then your job is to answer yes or no, whether there is any possible way you could place a ball on a billiard table and hit it so that it would bounce off those exact sides in that exact order. Of course, you could just guess, so to make it more challenging, let's say you're given a list of several sequences and you have to answer every single one correctly. To save time, I'll use the phrase billiard string for sequences that really could come from billiards. I'm using the word string from computer science to mean any sequence of letters, numbers, or other symbols. I'm going to put the answers to this game on the right-hand side in a moment, so if you want to try this yourself, you can pause the video or just cover up that part of the screen for now. We'll return to these strings later and see exactly how we can determine which ones could come from billiards and which ones could not. The idea of mathematical billiards has featured in videos by Numberphile, 3Blue1Brown, and many others. It also has applications to physics and other areas of pure mathematics. To be clear what we mean by mathematical billiards, we are always assuming that the ball moves in a straight line in between each collision. There's no spin and no trick shots. We also assume there's no loss of energy due to friction or drag. For this particular game, we are using a rectangular table, and we won't be worrying about the ball falling into any of the pockets. Lastly, we assume that the ball never exactly hits a corner because our strings only use symbols for the four sides. One thing we do not have to specify is the exact size of the rectangle. In fact, this does not matter. When a ball ricochets off a straight wall, its path makes two angles with the wall, the angle of incidence and the angle of reflection. Given our other assumptions, these two angles will be exactly equal. If we have a copy of this table, but we change the units in one of the directions, we definitely have angles that are different from our original table, but the new angle of incidence will still equal the new angle of reflection, so we can stretch or squish the entire picture without changing which sides are hit in which order. For this reason, I'll often draw squares, even though our results still work for rectangular tables of other dimensions. Ideally, we'd like to be able to win our game without having to read every single letter of every single line. If we can find specific pieces of text that will tell us that a string does not come from a billiard, that will make our game much faster. One rule that any billiard string must follow is that the L and R symbols should alternate back and forth. It's probably obvious that we can't have two L's in our string back to back, because a ball that hits the left ball twice can't be moving in a straight line in between bounces. But this rule actually says a lot more than that. If we have a much longer string and we look at only the L and R symbols in it, those should also alternate without ever having two L's or two R's in a row. To see why, think about what happens after the letter L in a string. After hitting the left wall, the ball will be moving somewhat to the right, possibly right and up or right and down, so the next time it hits a vertical wall, it will have to be the right wall, not the left wall. Therefore, if you ignore all the top and bottom hits, an L can only be followed by an R. Flipping this picture around, we see that after hitting the right wall, the ball must eventually hit the left wall before the right, so every R can only be followed by L. This is true even if there are hundreds of T and B symbols in between them. Similar reasoning shows that if we ignore all the L and R symbols, then the T's and B's must also alternate if the sequence does come from a valid billiard. We can now solve some of the tasks in our game. If we ignore all the T's and B's in our strings, we are looking for places where two L's occur without an R in between or two R's without an L in between. Among these 7 strings, this occurs only once, here in the second string. We now know that this string cannot come from a valid billiard. We can also look for places where the T's and B's do not alternate. Can you find any such places? This segment of the 4th string would require a ball to hit the bottom side twice without ever hitting the top side in between, and thus the whole string cannot come from a valid billiard. The only other error of this type comes later in the 4th string. Either of the underlined sections would be enough to know that the fourth string is not a valid billiard. In this case, we just have more evidence than necessary. Thanks to the alternation rules, we can eliminate these two strings as potential billiards, but it doesn't help us immediately with any of the other strings, since their T's and B's do alternate, as do their L's and R's. There is still a way to use alternation to help us with the remaining strings. Instead of having four symbols, L, R, T, and B, we can use one symbol for hits on a vertical wall and one symbol for all hits on a horizontal wall. We'll use 0 and 1 here simply because strings of zeros and ones are common in many other fields. If we didn't know about the alternating pattern, this kind of substitution could be dangerous. After all, there are multiple strings of LRTB that will become exactly the same string after we change to zeros and ones. So how can we be sure that a rule based on zeros and ones will actually help us with our original strings? Suppose this string of zeros and ones came from an actual billiard, which in fact it did. How do we deal with the fact that each zero might have been an L or an R, and likewise each one a T or B? Well, if the very first zero happened to come from an L, then we immediately know how to handle all the remaining zeros because we know that L's and R's must alternate. Similarly, once we know whether a single one came from a T or a B, all the other ones also become known to us. For this example, here's the beginning of an actual billiard path that perfectly matches this string. But what if that first zero wasn't an L? The only other possibility is that it's an R, and that means exchanging all of the L's and R's in the whole string in order to maintain the alternation. With the T's and B's the same, what we've done is to take our original path and use its mirror image. Likewise, the other options that could come from exchanging T's and B's correspond to other symmetric versions of the same path. If any one alternating translation of a 0-1 string back into L's, R's, T's, and B's corresponds to a valid billiard, then all of the alternating translations do. That's why it's okay to just deal with strings of zeros and ones now. Recall that we had 5 strings of LRTB for which we don't know whether they come from billiards or not. We will now replace all of the L's and R's with zeros and replace all of the T's and B's with ones to get 5 strings of zeros and ones. These are what we need to analyze. One of the most common ways to analyze a string in information theory is to look at its substrings, that is, all of the strings that appear somewhere within it. As an example, let's look at the substrings of 0, 0, 1, 1, 1, 1, 1, 1, 0 that have small lengths. There are only two substrings of length 1, the string 0 and the string 1. For substrings of length 2, we can imagine a small window 2 characters wide that moves across the main string. This is a nice way to make sure we don't accidentally miss any substrings. The same idea can be used for substrings of length 3, and indeed for any size substring we might want. We will also be interested in what we call the weight of a string or substring, which we define as the number of non-zero characters in the string. Because we are using only 0 and 1 in our strings, this is also equal to the sum of all the digits in a string. Here are several examples of strings and their weights, which are hopefully perfectly clear. Now that we know what the weight of a string means, we can give the following definition. A string is called balanced if any two substrings of the same length have weights that differ by at most 1. This definition is not very intuitive to me, so I want to go through some examples very carefully. For the 3 strings shown here, do you think they're balanced or not? You might want to write down your first impression or intuitive guess of whether these are balanced, and then compare that to the actual answer that we get from using the definition, which we'll now walk through together. The definition of balanced talks about substrings, so let's write out some of the substrings for this example. Then we need to look at substrings that have the same length. There are only 2 substrings of length 1. Their weights are 0 and 1. Those weights are no more than 1 apart from each other, which is exactly what we want. The substrings of length 2 have weights of either 1 or 2 depending on the substring, so if you look at any 2 of them, their weights will differ by at most 1. For length 3, it's even easier. All of the substrings of length 3 have weight 2, so any 2 substrings of length 3 will have weights that differ by 0, and that's all right. To really be sure that the string on the left is balanced, you would need to look at all the substrings of length 4, 5, 6, and 7. I'll show length 4 on the screen, and you can test the longer substrings if you want. In the end, this string is balanced. The next example is actually much easier. There's only one substring of each length, so any two substrings of the same length will have exactly the same weight, in other words, weights that differ by 0. Any string where all of the characters are the same will always be balanced. Our last example is much longer and maybe a bit more surprising. If you looked only at the substrings of length 3, the weights work perfectly nicely. But if you look at substrings of length 2, you'll find 3 different weights, which can never happen for balanced sequences. In fact, any string that has both 0, 0 and 1, 1 as substrings cannot be balanced, because those are two substrings of the same length, which have weights that differ by 2. The string on the left is not balanced, nor is the much simpler example of 1, 1, 0, 0. We now have two potential ways to classify a string, whether or not it comes from a billiard and whether or not it's balanced. In order to win our game, we need to be able to recognize billiard strings, so we'd like to know how these two categories are related. In other words, what this Venn diagram really looks like. It might be that billiard strings are a special type of balanced string. In that case, we could eliminate any strings with zeros and ones that weren't balanced, similar to how we eliminated LRTB strings that didn't follow the alternation rules. We would still need something else to know whether a balanced string actually came from a billiard or not. Another possibility is that balanced strings form a proper subset of billiard strings. In this scenario, we would finally be able to answer yes to certain strings in our game, but we would still need a way to detect any billiard strings that were not balanced. You might wonder whether there's any overlap at all between these two categories. A simple example of a ball hitting the top and then the bottom actually answers this. Its original string is TB, and under our substitution, both of those letters become 1s. The string 1, 1 is definitely balanced, so there is indeed some overlap between these two categories. The final possibility is that the set of billiard strings with zeros and ones is exactly the same as the set of balanced strings with zeros and ones. This actually turns out to be true. To explain why requires a lot of work, so I'll save that explanation for a follow-up video. As a preview, it will involve unfolding a billiard path into a straight line and looking carefully at how the slope of that line affects the string. For now, we'll just use this amazing fact to finally win our game. To remind you, we first check our rules about alternation. The second sequence has two L's with no R in between, and the fourth sequence has cases where the T and B symbols do not alternate correctly. Strings that fail these alternation tests cannot come from billiards. For the strings that do alternate correctly, we convert them into strings of zeros and ones and check whether those strings are balanced. Any sequence that has both double 0 and double 1 as substrings can't be balanced. For the remaining strings, we could check the definition of balanced by looking at every possible substring of the strings, but there are some shortcuts we can take. Because the remaining strings have no double zeros and no double ones, they must either consist of groups of ones in between individual zeros or groups of zeros in between individual ones. The size of these groups can be used to determine whether each string is balanced without looking at every single substring. For example, the fifth sequence has a group of 3 zeros with ones on either side and a group of 5 zeros with ones on either side, and this will imply that the string is not balanced. The group of 5 zeros is a substring of length 5. The group of 3 zeros could be considered a substring of length 3, but the definition of balanced does not compare substrings of different lengths. What we need to do is include the ones that are on either side of the group of 3 zeros. This gives us two substrings that both have length 5, but one of them has a weight of 2 while the other has a weight of 0. The whole string, therefore, is not balanced. The remaining strings have groups of only two sizes, ignoring any groups on the far left or far right, but that does not necessarily mean that they are balanced. With a little more work, we could show that the third string and the final string are balanced, but the second to last string is not. For the second to last string, these two substrings both have length 5, but their weights are 1 and 3, which do not differ by at most 1. The question of whether a string of zeros and ones is balanced has exactly the same answer as whether that string could come from a billiard, so we now know with certainty which of these examples came from billiards and which did not. Congratulations on winning this unusual game.